Hi, I'm Ravital, and I'm the founder of Sunscreen, and today we're going to be looking at the landscape of fully homomorphic encryption. So in terms of what you're going to hear in this talk today, we'll talk a little bit about what fully homomorphic encryption is. We'll look a little bit at homomorphic encryption, which you've almost certainly used before. We'll talk about why you should care about FHE, both in Web 2 and Web 3. We'll talk a little bit about how FHE has evolved over the years, why FHE is really difficult to use, how to make FHE easier to use, and finally, what Web 3 and FHE have to do with one another. So to start us off, let me explain what fully homomorphic encryption even is. So fully homomorphic encryption allows you to perform computation directly on encrypted data. So by computation, we specifically mean addition and multiplication. And in terms of FHE, you can think of it as an extension to public key cryptography. So with public key cryptography, you can only share data in some secure way. You can't actually do anything with your encrypted data. With FHE, you're able to perform computation directly on your encrypted data. So in the image below, we can imagine putting some encrypted data into a program and then running that program directly on our encrypted data to get some encrypted outputs. Just to clarify, fully homomorphic encryption is focused on data privacy. There is nothing to do with anonymity here. So if you're interested in hiding identities, you'll need to combine FHE with some other technology. While you probably have not used an FHE scheme before or seen one deployed in practice, you have almost certainly used a homomorphic encryption scheme before. So what's the difference between FHE and homomorphic encryption? With homomorphic encryption, you are only able to do one type of computation on encrypted data. Either you can do addition or multiplication on encrypted data. FHE, on the other hand, allows you to do both addition and multiplication on encrypted data. So where might you have encountered a homomorphic encryption scheme before? Probably in one of the older versions of TLS that made use of RSA, which is a homomorphic encryption scheme, or potentially with the El-Gamal encryption scheme, which is also a homomorphic encryption scheme. In terms of why you should care about fully homomorphic encryption, let's look a little bit at the applications in Web 2. So one interesting application is the ability to do analytics on private data. So you can imagine creating a private version of 23andMe where only the user would know the results of tests run on their genomic data. Another application that's received a lot of interest in Web 2 is private inference. So imagine having some trained machine learning model and being able to run that model on encrypted user data. Finally, another application that's receiving quite a bit of interest on academia is private information retrieval. And that would allow you to retrieve an item from a database without revealing to the server which item you're interested in retrieving. In terms of the Web3 applications, some interesting use cases of FHE include private smart contracts, so the ability to run smart contracts on encrypted data. There has been quite a bit of interest in private shared state. This would require combining FHE with some other tools, but it's very interesting for both decentralized exchanges and auctions. And finally, there's quite a bit of interest in applying private information retrieval into Web 3 as well, where you'd be able to look up an addresses balance privately. A quick warning. People think of privacy technology as being only good, but it turns out that FHE could actually be used for some fairly evil purposes. There was an interesting publication in Usenet Security 2021, and the idea here was that you can associate a hash with any image. Say that hash is encrypted with respect to an FHE scheme. You would actually be able to detect what sorts of images people have shared in end-to-end encrypted messaging. And this could be used both to identify harmful media, or it could also be used by surveillance states for censorship purposes. Let's take a quick look at the history of FHE. So in comparison to other privacy technologies like zero-knowledge proofs and multi-party computation, FHE has had a much shorter time to develop. The idea of FHE itself is from 1978, and it took over 30 years to construct an actual FHE scheme. That was done in 2009 by Craig Gentry. Unfortunately, the first generation of FHE was incredibly slow. It took over 10 minutes to multiply two encrypted numbers together using Craig Gentry's original FHE scheme. A couple years later, there was the second generation of FHE. It brought down the time significantly. So what used to take many, many minutes was brought down to milliseconds. With the second generation of FHE, we were able to do fairly fast arithmetic on encrypted data. The continuation of FHE was in 2016 with this improved second generation schemes. So we saw CKKS, which allowed for even faster arithmetic on encrypted data at the cost of having some scaling issues. And then finally, today we're at the third generation of FHE with the TFHE scheme, which allows for very fast comparisons on encrypted data at the cost of not being able to support fast arithmetic on encrypted data. In terms of why nobody is using FHE, there are two major reasons. FHE has had a fairly short time to develop in comparison to zero-knowledge proofs and MPC. So at this point in time, it's not a very good fit for many applications. It's fairly inefficient as far as anyone's concerned. There is a very large data blow-up. So if you imagine taking some data and encrypting it with respect to an FHE scheme, it often blows up the data size by 10,000x or larger. It is fairly slow. So in terms of doing computations with FHE, you can imagine 100,000x or worse overhead for running that computation. And finally, in terms of what the schemes currently offer, you can either get fast arithmetic or fast comparisons, but there is no scheme that gives you both. So those trade-offs can be pretty limiting for real-life applications. Even if you're okay living with all of these downsides to FHE, it turns out that FHE is actually really, really hard to use. So with FHE, a big problem in terms of efficiency is picking parameters. And it turns out that picking parameters is both an art and a science. There are many trade-offs to consider. You have to think about ciphertext and public key sizes. You have to think about what sorts of computations you want to do. And you have to also think about performance. In terms of setting up the parameters themselves, you need quite a bit of background in math. You need to know abstract algebra to effectively set the parameters. And finally, there is a big performance difference depending on how well you select parameters, which makes FHE very challenging. So how can we make FHE easy to use? The idea itself is pretty simple. What if we build a compiler? In terms of what an FHE compiler would offer, you can imagine it would take a regular developer's program, say written in Python, Rust, C++, and it would turn it into its FHE equivalent. In terms of what that compiler would actually do, it would help you pick the parameters for the FHE scheme. It would help you set up circuits, because it turns out FHE requires understanding either arithmetic or binary circuits. It would help you with data encoding, and it would help you with inserting these special FHE-specific operations that help you manage some of the efficiency issues. There have been a number of compilers built. The very first one was 2015, Chingulata, but unfortunately, most of the FHE compilers at this point in time are focused on machine learning applications. So can we do TensorFlow computations on encrypted data? Can we do NumPy computations on encrypted data? In terms of why these FHE compilers haven't really gone anywhere and nobody's using them, it turns out they're missing some pretty important features. For one, all of these compilers tend to introduce a pretty large performance overhead. So I've told you that FHE is slow, but these compilers make FHE a lot worse. You might see 100x, 1000x, 10,000x overhead from using a compiler versus handwriting the code yourself. A number of these compilers are still lacking in terms of usability. So they may help you with setting some of the scheme parameters, but they expect you to be able to set some of them yourself. Finally, a lot of the compilers are very focused on particular domains or applications. So there are currently no compilers at this point in time ready for deployment for Web3 specific applications. We've talked a little bit about general challenges in making FHE work for both Web 2 and Web 3, but it turns out bringing FHE to Web 3 is a lot harder. So to start us off, let's talk about what kinds of developers what kinds of needs Web3 developers have. We certainly need to work with a scheme that offers high precision. It will not be okay in most use cases to say someone's lost 1 ETH because we've lost precision. We will almost certainly want to think about composing smart contracts, so feeding encrypted data from one smart contract into another, and we will have to do arbitrary computation on encrypted data. There is no way to know a priori how many transactions you plan to engage in. The issue here is that there is no FHE compiler for Web3 applications currently available that satisfies all of these features. And it turns out there's even more challenges in using fully homomorphic encryption on blockchain. For the very first challenge, the issue with making use of FHE in Web3 is that we're working in a trustless setting. So what does that mean in practice? Well, if you're feeding encrypted data into an application, I'm feeding encrypted data into an application, how do we know that the other person's encrypted data satisfies the conditions of that application? We don't. So another piece of technology has to come to play here. We need zero-knowledge proofs. The challenge here is that FHE uses something called lattice-based cryptography. The most efficient zero-knowledge proof constructions don't. How do we combine these two technologies and get good performance? That is a pretty challenging issue. The next problem has to do with storage. It turns out that FHE, although it can in theory be quite fast, it is never space efficient. So for the sorts of applications you'd be interested in Web3, you're likely going to end up with ciphertext that are tens of kilobytes to hundreds of kilobytes in size. Can you possibly store that directly on chain? Probably not. So where could you store them? That's kind of unclear. Let's take a little bit of a look at what people are currently working on when it comes to FHE and Web3. So we have a number of companies, both big and small, trying to build better FHE libraries, more optimized FHE libraries. There are some folks, specifically us, working on building an FHE compiler aimed at some of the needs of Web3 developers. We are also working on zero-knowledge proof tooling that is compatible with FHE and provides decent efficiency. There are some other folks working on private address balance lookups. And finally, there's been quite a bit of interest both from big companies and startups in building hardware to speed up fully homomorphic encryption. And hopefully other people will join us in the space as well. And that's it. Thank you.